In this lecture, we are going to see how the stagnation properties and the Mach number relates to the area change and how it is affecting the flow in a compressible scenario. So, what I am going to discuss is the variable area changes that is going to affect the density and the velocity. Adiabatic flow. Okay. So, I have a situation where the flow is through some duct where the area is changing. So, I have a velocity v1, I have a velocity v2, and what are the changes that is going to happen here in terms of Mach number and density. I assume Q is 0, so no heat transfer. Ws is 0, so no work done, no shaft work. No losses. Essentially, I am trying to do 1D flow. So, this is an isentropic process. So, what I am trying to do here is an isentropic flow through a variable area duct. So, I write the energy equation in the differential form. This would be dq equals dh plus dws plus dv square by 2 plus dg dz. I also assume no potential. So, my heat transfer is 0, shaft work is 0, potential energy is 0. So, I am left with dH equals minus dV square by 2. That is my equation 1. From Gibbs relation, T ds equals dH minus V dP. ds is 0, so 0 dH minus dP by rho. This is my equation 2. From which I will get dV square by 2 equals dP by rho minus or V dV by 2 would go V dV equals dP by rho. This equation is now substituted in the continuity equation. Which we have already seen in this form. So, I will substitute dV by V here. So, d A by A plus d rho by rho minus dP by rho v square equals 0. So, I have replaced dV, the changes in velocity, in this form. Okay. So, my aim is to represent this in terms of Mach number. Okay. dP by rho equals dA by A plus d rho by rho multiplied by v square I know A square is dP by d rho, which is at constant entropy. So, that is the velocity of sound. Again we have seen this before. So, I use that relation here in this and obtain these quantities in terms of Mach number. I would change my dP as d rho into A square. So, I substitute this is equation 4 in here. So, your dP is now d rho into A square by rho equals v square into dA by A plus d rho by rho, which is m square into dA by A plus d rho by rho. Now, I take d rho on this side. So, that would be d rho by rho into 1 minus m square equals m square by dA by A. I would end up in relation d rho by rho equals m square by 1 minus m square into dA by A. So, the changes in density related to changes in area in terms of Mach number. So, I will rewrite this equation here and we will collect all those equations and we will try to discuss some physics with these equations at the end of the lecture. So, we have the first equation d rho by rho equals m square by 1 minus m square into dA by A. Now, I substitute this equation in the continuity equation in the log form. So, I go back to the continuity equation. dA by A plus dV by V plus d rho by rho equals 0. d rho by rho is now replaced by this equation, which I now call it as A. Substitute equation A, I would get dA by A plus dV by V equals plus m square by 1 minus m square into dA by A equals 0. So, I take dA by dA outside and 1 plus m square by 1 minus m square plus dV by V equals 0. So, I can write my dV by V in terms of Mach number and area change. dV by V equals dA by A by 1 minus m square 1. So, I can take this equation and write it down here for discussions later in the curve. There is a minus sign 1. Yeah, okay. So, this is my equation B. We have also seen this equation dP by rho equals dA by A plus d rho by rho into V square, where I substitute now my dV by d rho by rho from this equation here. So, dA by A plus d rho by d rho by rho is m square by 1 minus m square into dA by A into V square. So, this is dA by A, is again 1 by 1 minus m square into V square, okay, dP by rho. So, that is the equation for pressure change, which again I will write it down here. From equation A and B, from equation A and B I can eliminate my dA. So, d rho by rho equals m square by 1 minus m square is 1 minus m square into dV by V with a minus sign. So, this is nothing but m square minus m square dV by V. So, I take that equation here. Equation C. So, all we have done here is modified the continuity equation. We take an isentropic flow and we have modified those equations with the area change and the velocity changes along with the Mach number relation. Now, we will try to see what does this physically mean. So, let us take first the equation B. So, dV by V equals minus dA by A 1 minus m square. If m is less than 1, if m is less than 1, this quantity is positive, 1 minus m square is positive, which means my dV is minus, goes as minus dA. So, if there is a positive change in dV, there should be a negative change in dA. So, what is dA? So, if I have a converging area like diverging area like this, my area is increasing, area A is increasing along with the flow, which means my dA is positive. So, if dA is positive, then my dV is negative. So, for a condition where m is less than 1, my area increases means my velocity should decrease. For m less than 1, area increases would result in velocity decrease and vice versa. So, if for m equals 1, if area decreases, result in velocity increase, which means a scenario like this, my area is decreasing, my velocity increases if m is less than 1. Now, this is something which we have already learned in our incompressible flow. When you have a water, you use your continuity equation and you find that the velocity is changing according to this. So, this would be a diffuser, that would be a nozzle. Now, if m is greater than 1, m is greater than 1, what happens? If m 1 minus m square is negative. So, m is like greater than 1, this quantity is negative. So, your total on the right hand side is positive. So, your dV by V is now positive quantity with dA by A. Okay. So, your dV goes as dA. The sign of dV is the same as the sign of dA. So, if there is an increase in area, there is an increase in velocity. If there is a decrease in area, there is a decrease in velocity. So, that is different from what you have seen in your incompressible flow or your subsonic flow in this case. So, this is subsonic, this is supersonic. So, I have this is decrease in area, velocity will also decrease if my m is greater than 1, and this area increasing, my velocity also increases. That is from equation B. So, these inferences we have deducted from equation B. Likewise, you can think of the equation A, where the area changes is related to your density changes. Now, before going to equation A, look at equation D. So, in equation D, if your Mach number is much less than 1, it is very small, okay. Your m square is also going to be very small, okay. So, your d rho changes due to dV is nearly small. Is now very small if the Mach number is very small. This is the case of incompressible flow. Where we assume the density changes due to your velocity change is very small. So, in such a case we can infer that if m is less than much less than 1, this will approximate to incompressible flow. So, if your density change is very small, for m equals a very small quantity, if I go back and look at equation B, equation B is dV by A equals dV by V equals minus dA by A into 1 minus m square. Now, m square is very small. Okay. So, your balance is now between velocity and area. So, at m equals very small case, your density changes are very small, your balance is between velocity and area. Okay. Now, if you look at the other way around, if m is large, or let us take m equals 1. If m equals 1, let us take the first equation. M equals 1, here 1 minus m square into d rho by rho equals m square dA, or if I take the next equation 1 minus m square equals dV by V equals minus dA by A. Okay. So, this is equation A and this is equation B. So, if m equals 1, it just means that your dA is 0. Okay. So, that is what we call as the throat condition, which we will discuss it in a later lecture. So, here the area change is small. So, the adjustments are all between velocity and density. Okay. So, at very small Mach number, we see the balance is between velocity and area, and in the large Mach number or at Mach number 1, the balance is between density and V. Okay. For all other condition, it is a balance between density, velocity and area. Okay. So, that is the difference between incompressible flow and the compressible flow. The concept has to be slightly modified, and these are all valid if the process is isentropic. So, all this have been derived from the continuity equation alone with the assumption of isentropicity. If it is not isentropic, there will be small changes here. Okay. So, that is the message that you get from these equations. So, essentially what we have done here is we have taken the continuity equation, we have used the isentropic condition into the continuity equation. You derived these 4 equations, where you can find the changes in pressure, density, velocity and area, all related to Mach number. Okay. That is the discussion on variable area adiabatic flow. Next class we will try to see how this affects the flow through a nozzle or diverging and converging nozzles. Okay.